Welcome. In this video we're going to introduce the singular value decomposition for matrices. Our objectives are first to define the singular value decomposition. We'll look at the skinny SVD form and also write the singular value decomposition as a sum of rank 1 outer products. Then we'll explore the use of the SVD to find the best low rank approximation for a matrix and interpret a matrix as an operator in terms of the parameters in the SVD. Now the SVD has an enormous range of applications because this is a particular matrix decomposition that leads to very good low rank approximations to matrices. So any n by m matrix A can be factored as a matrix U, which is an n by n matrix and has orthonormal columns, times a diagonal matrix sigma, which is n by m, and it has positive elements on the diagonal, and times a matrix V transpose, where V is an m by m matrix, and it also has orthonormal columns. Now there's two different forms for sigma depending on whether n is greater than m, in other words the matrix is taller than it is wide, or m is greater than n, which would be the case where the matrix is wider than it is tall. If the matrix is taller than it's wide, so the m by m matrix containing the diagonal is on top of a whole bunch of zeros. In the other case, where m is greater than n, then the diagonal ends here on the left, and on the right we have a matrix of zeros. Now a very important part of the definition of singular value decomposition is that the individual singular values, sigma 1, sigma 2, and so on, that they are ordered from largest to smallest, and they're also positive. This is very important for how we're going to use the singular value decomposition. It's really useful to get a pictorial representation for the singular value decomposition in these two different cases of a matrix which is taller than it is wide and a matrix which is wider than it is tall. And in this case, n is greater than m, so U is going to be an n by n matrix. Then sigma is n by m, so that's at the same dimension as A. And then V is a square matrix of m by m. Now in the other case, where A is wider than it is tall, then U is an n by n matrix. Sigma again has the same dimension as A. And then in this case, V transpose is the m by m matrix. Now the fact that sigma has a block of zeros on the lower part for the taller case and on the right for the wider case leads to a simplification. We're going to call that the skinny SVD. Well, when I do the matrix multiplication with U, the rightmost columns of U are going to be multiplied by all these zeros. So these rightmost columns really don't matter. They get zeroed out when they get multiplied into here. So I can write A equivalently in terms of an n by m matrix U, an m by m matrix sigma, where I've eliminated the block of zeros, and then the m by m matrix V transpose. Similarly, in this case, my sigma has a block of zeros on the right side, and those zeros, when I multiply sigma times V transpose, those zeros are going to interact with the lower rows of V transpose and are going to eliminate those rows from any contribution. So I can write this as U, an n by n matrix, times a square diagonal matrix, which is n by n, times a matrix V transpose, which has the same dimension as A. In other words, I've discarded all the bottom rows of V transpose that I had over here on the right. I've chosen not to use separate notation for these two cases right now because the context will generally always indicate whether we're working with the full SVD or the skinny SVD. Most of the time we're going to be working with the skinny SVD. So far we've been writing the singular value decomposition in terms of products of matrices, but it's very useful in many situations to expand these matrix products and write this in terms of the vectors that compose U and V. We'll let the columns of the matrix U be denoted by vectors U1, U2 through UM. The diagonal matrix sigma with elements sigma 1, sigma 2 through sigma m, the matrix V, whose rows are V1 transpose, V2 transpose, VM transpose. So this is the skinny SVD for the case where A is taller than it is wide, which is often the case that we work with in machine learning. View these as block matrix multiplication. This first column gets multiplied into the first row of sigma, and since the only element in the first row is sigma 1, the result is sigma 1 times U1. And so that then is going to get multiplied into the first row of V transpose, which is V1 transpose. And so I'm going to have U1, sigma 1, V1 transpose, plus the second column into the second row of sigma, so that's going to be U2 times sigma 2, times the second row of V transpose, which will be V2 transpose, until I get to the last column of U times sigma M times the last row of V transpose, or VM. In this sum of outer products form, I'm going to represent the singular value decomposition of A as the sum from I equals 1 to M of sigma I times UI times VI transpose. Now UI VI transpose is a rank 1 matrix. And so what I'm writing A in terms of a sum of capital M rank 1 matrices, which are each n by m. Now the singular value decomposition gives us the best low rank approximation to a matrix. And to define what we mean by best, we're going to introduce something called the Frobenius norm, which is a norm that's applied to matrices. So if I have matrix A, then the Frobenius norm squared is going to be just the sum of the squares of all the elements in that matrix. This is equivalent to taking the matrix A and taking the individual columns, stacking them up on top of one another to make one really long vector, and taking the 2 norm squared of that vector. So the Frobenius norm is what we're going to use when we define the best low rank approximation. And that's obtained using the Eckert-Young theorem, which was proved in 1936. So we're going to let A be a rank R matrix, and we're going to assume that K is less than R. Find a matrix B, which is rank K, so that that rank K matrix is as close as possible to the rank R matrix A. If I search over all matrices B whose rank is K or less, then the minimum of this Frobenius norm, remember we're just taking the sum of the squares of all the elements in the difference between A and B. And that's going to be equal to the sum from I equals K plus 1 to R of sigma I squared, when the matrix B is equal to the sum from I equals 1 to K of sigma I UI VI transpose, where U sigma V transpose is the singular value decomposition of the matrix A. It's telling us that this matrix B is the best rank K approximation to the matrix A, and that is obtained using the singular value decomposition. And this is a very powerful result. Furthermore, it's also telling us the size of the error between A and B. It's determined by these singular values that we exclude from our representation. So what we're doing is we're taking some matrix A, and I'm writing A, or approximating it, as sigma 1 times U1 V1 transpose plus sigma 2 times U2 V2 transpose. And since we're assuming this is going to be a rank K matrix, then I have K terms here, and that last one will be sigma K UK VK transpose. Now I'd like to think about this is that each one of these matrices make up one component of A. U1 V1 transpose describes a set of patterns that are associated with A. U2 V2 transpose describes another set of patterns, and UK VK transpose describes the kth set of patterns. So if I look at each of these individual terms, the columns of each of these terms are given by the corresponding U, and then that's just going to be scaled by different constants that are in the V1. On the other hand, if I look at the patterns in the rows of each of these matrices, each row is a scaled version of VI transpose. So UI and VI determine a pattern associated with a particular component of the matrix A in this SVD representation. Now, because the error is given by the sum of the singular values that are excluded, and remember that the singular values are ordered from largest to smallest, so sigma 1 is the largest singular value, then I can define U1 V1 transpose and say that this is the most important pattern for representing the matrix A. Sigma 2 is the second biggest, so U2 V2 transpose is the second most important pattern for representing the matrix A, and so on. So these sigma I provide an ordered ranking of these components that constitute the matrix A. Machine learning is all about finding patterns in data. And when we're looking for patterns in data, we want to find significant patterns. So having these singular values can tell us that this pattern associated with sigma 1 is much more important, say, than this pattern associated with sigma k, and the relative importance is determined by the size of these singular values. Now, it's common to plot the singular values as a function of their index. Because they typically have a large dynamic range, people often plot the log of the singular values because that will compress the dynamic range. A lot of data matrices, you'll see that the log of the singular values are fairly constant, then at some point there's a big drop off. In other words, the singular values are getting very small. And so if I ask, what's a good low rank approximation, or how many patterns do I need, patterns that are associated with singular values that are really small don't make a significant contribution to the approximation of the matrix. So if these sigma i's from k plus 1 to r are close to 0, then my matrix B is very close to A. We typically want to represent the matrix A using k terms that capture the significant singular values. And this kind of a plot can help us see where do the singular values begin to fall off and how many terms do we need to represent the matrix A relatively well, and we'll look at this more later. And we're going to conclude this video by looking at what the singular value decomposition tells us about a matrix acting as an operator. Now, when I say that a matrix is acting as an operator, what I mean, A operates on X to give me Y. Since A is n by m, then X is going to be an m by 1 vector, and A maps this m by 1 vector into the n by 1 vector Y. If I replace A by its singular value decomposition, use sigma V transpose times X, then we can group terms in the order in which they're applied. So first, I can think about in blue V transpose X, then in green I can think about sigma times V transpose X, and then in orange I can think about U times sigma V transpose X. So we're starting off in the space of m-dimensional reals because X is an m-dimensional vector. The operation by V transpose, it turns out, is simply a rotation of the vector X. The fact that V transpose affects the rotation is evident by considering the norm of V transpose X squared. So the 2 norm squared is just the inner product of this vector with itself, so that's X transpose V, V transpose X. Since the columns of V as well as the rows of V are orthonormal, V transpose is the identity, and we see that this 2 norm of V transpose X is the same as the 2 norm of X. So when I multiply by V, I'm not changing the length of X at all, I'm just pointing X in a different direction. That's why we're calling this a rotation. So now I have this vector V transpose X, and I next apply sigma, the set of operations in green. Well, sigma is a diagonal matrix, and so it's going to have the effect of scaling each dimension of V transpose X. And then finally, we apply U, which has orthonormal columns, so again, that has the potential to be a rotation, but in this case, because U is taller than it is wide, we are also increasing the dimensions. So we're mapping from an m-dimensional space into an n-dimensional space. We'll illustrate this series of operations for the case where A is 3 by 2, and so we're starting with X in 2 dimensions, and we're going to end up with a Y in 3 dimensions. So if we have some vector X, and we can also look at the set of all vectors X whose 2 norm squared is equal to 1, and that'll be a circle. V doesn't change the length of X, so it's only rotating X. So we'll have V transpose X, the identical length vector, but pointing in another direction. And since V is not changing the length of X, it's not changing this circle, which represents the set of vectors now in blue that have 2 norms squared equal to 1. Now then we apply the matrix sigma to get to the green case, and sigma scales the 2 components of these vectors. So sigma 1 scales along this axis and sigma 2 scales along this axis, and that's going to cause the relative length of the 2 components to change. So here I've shown V transpose X with the first component longer and the second component a little shorter. And if we look at the set of all vectors for which sigma transpose V transpose X has unit norm squared, it turns out that will be an ellipse. Now finally, we're going to apply the matrix U, which will rotate and convert from 2 dimensions to 3. So any vector y has to lie in the span of U, and since U has 2 components, that span defines a plane. So this vector that we had in green is going to be mapped into some new vector which is the same length as it was in the green case, but now is pointing possibly in a different direction and is located in this plane. And our ellipse also will be tilted so that it lies in the plane associated with the span of U. Now this leads us to something called the operator norm of a matrix, which we will find use for later as well. We can write that as the 2 norm, or it's also written as the operator norm, and it's defined as the maximum vector x not equal to 0, the 2 norm of ax divided by the 2 norm of x. So we can think about this as that I have some vector and has a certain length, then I'm going to define the operator norm to be what is the greatest stretching I could apply to any vector x by the matrix A. It turns out this is given the largest singular value, sigma 1. And there's a proof of this in the notes that accompany the video. So there's a lot of information in this video. There's a lot to learn about the SVD, and we'll continue this process in subsequent videos.